This meeting is being recorded.
All right. So, hello everyone. Welcome to episode 36 of Warsaw Quantum Computing Group meetup. Today we have two speakers, Julia Plewa and Joanna Sieńko, and they will give a talk titled Comparison of Quantum Optimization Algorithms and Encoding Schemes for Workflow Scheduling. Before we start, we would like to thank our strategic partners, Starto and Cogit, for supporting us, and also thanks to our honorary partners for supporting promotion of our meetup. So as usually, this meeting is recorded. So if hopefully the video will be available on our YouTube channel. If you have any questions during this talk, please post your questions on our chat. So if there are some urgent questions, we'll try to interrupt, but there will be also a Q&A session at the end. So I think that's all from my side for now. I will now stop sharing my screen. And Julia, Joanna, first of all, thank you for accepting our invitation. It's our pleasure to have you with us. And if you are ready, the Zoom is yours, so we can start.
Okay, thank you. I'll share my screen. It should work.
Yes, I can see your screen now.
Okay, so hello everyone. My name is Julia Plewa. We'll be presenting the results of our master's thesis. This presentation is called, as was already said, Comparison of Algorithms and Encoding Schemes for Workflow Scheduling. It was a shared master's thesis between me and Joanna Sieńko, and our supervisor was Dr. Engineer Katarzyna Rycerz, who actually spoke about the same problem 2 weeks ago, but she sort of spoke about a different aspect of it. So hopefully this will still be interesting to you. So the agenda for today is the following. We'll begin by discussing the goals of our thesis. Then we'll define two important concepts, which are workflow scheduling and hybrid algorithms, because both those terms appeared in the title of our master's thesis. Then we'll move on to discuss the improvements that we made to the previous implementations, which were both encodings, different types of encodings, and QAOA mixers. Finally, we'll move to discuss the experiment design and then the results and conclusions and future work. So the goals of our thesis were to, first of all, analyze and improve the existing implementations of the workflow scheduling problem, because in the past, some other master's projects also tackled this problem. So we wanted to base our work on what was already done, so to avoid reinventing the wheel. We wanted to implement and compare different encoding schemes. That was one of the main goals, because the idea was that we would want to try solving larger problems. The original implementation only relied on a variation on one-hot encoding, and there are other more dense encoding schemes that can be used, and this way larger problems can be approached. We also wanted to test the performance of two algorithms, specifically QAOA and VQE. In the past, only VQE was used. We also experimented with different classical optimizers, and we introduced custom QAOA mixers as well to see if they would help. And finally, we wanted to test the efficacy of the implementation using a quantum computer simulator and noise models based on real hardware. Initially, we wanted to use a real quantum computer, but the IBM Melbourne machine, which had 16 qubits, was switched off, and we were sort of hoping to use that one. But then, like currently, I believe the largest available machine is around 7 qubits, which wasn't really enough for what we planned. So the workflow scheduling problem is defined as follows. This is our definition. It's a bit similar to what Dr. Rycerz talked about 2 weeks ago, but we sort of changed up the definition a little bit to make it more versatile for the different types of encoding. So the idea is that there are n tasks and m types of machines. We also have a graph that describes the ordering of the tasks. So in this case, task number 1 has to be executed before these two, And then task 4 can only proceed when task 2 and 3 are completed. And it's a directed acyclic graph, so there's no cycles. We also have two matrices, matrix C and T, which define the cost and the time of executing specific tasks on specific machines, because both the time and the cost can be different for each machine. And we have a deadline D. And so the goal is to minimize the overall cost of executing all tasks while maintaining the required order and meeting the deadline. So what we're actually minimizing is the cost, but we also have to fit within the deadline. So it doesn't matter if the whole thing gets executed in 5 minutes or 5 hours, as long as it's below the deadline. What we're actually minimizing is the cost. This is actually quite important, and I'll talk about it in more detail on the next slide. So this is the entire objective function for this problem, and I'll maybe I won't be getting into it that much, but I'll try to tell you what each component is about. So first things first, the algorithm's output is a one-dimensional vector, as they tend to be with quantum computers. But for the purposes of this definition, we're splitting up the one-dimensional output into two matrices. The first one is called X here, and it contains a 1 at index ij if task A is to be run on machine of type J. So it's just like one hot, like a vector of one hot vectors, basically, because every task can only be run on one machine type. Oh, also I forgot to say that here, when it says machine of type, basically the idea is that there is types of machines, but within each type there's an unlimited number of machines that's available. But there's m types. That's a pretty important distinction, because in this problem it's impossible for we don't have to make sure that each machine is free at every, not free, but we don't have to make sure that only one task is being run on a specific machine, because there's no, the number of machines isn't limited. It's just the number of types. So that's matrix X. And then the rest of the output of the algorithm is called Y here. And it determines the value of slack variables. And slack variables are very tricky. Were very tricky for us. They're necessary because we have an inequality here. As I said, the deadline doesn't have to be minimized. It just has to be met. So it doesn't matter how fast everything's executed. It just has to fit within the deadline. So since this is a function that we're minimizing or optimizing, whatever we call it, it wasn't just possible to add the time of execution to the cost, because this way quicker solutions could be prioritized over cheaper solutions. And the goal was to actually look for the cost. So the slack variables are used because of this inequality, and we have to have separate slack variables for every path. So in this case, we would have 2 paths to go from the first task to the last task. And for each path, we would have to make sure that we're fitting within the deadline. That's the approach to this that we sort of borrowed from our predecessors, to be honest. And yeah, so we can look at it briefly at each component. This first component, it's just the cost matrix multiplied by this X matrix. So this is just the cost. That's the main objective, and these 2 other components are the constraints, but they're also expressed as parts of this objective function, right? Because they're all summed up. The second component is a bit wild, but this is the deadline constraint, basically. So here we're looking at each path separately, and for each path we're making sure that we are below the deadline. So this is the deadline. Here we're calculating how long it takes to execute the entire thing, and here we're adding these slack variables, and so this will have its minimum when 0, basically. So when the sum of the execution times and the slacks are equal to the deadline. So that's this whole part, and it has to go path by path. And this last portion is encoding dependent, but in general, this is the constraint that ensures that the encoding is correct. So for one-hot encoding, it would be making sure that each task is run on only one machine type. This changes a bit depending on the encoding. For instance, for binary encoding, it's possible to skip this altogether, because if we're using binary encoding and for instance, we want to encode the states 0, 1, 2, and 3, and we have 2 bits, there's no incorrect states, right? Because there's 0, 0, 0, 1, 1, 0, 1, 1. None of them are incorrect. So in this case, it would be possible to just skip this altogether for one-hot encoding. And domain wall encoding, which is the third type we looked at, this has to have its specific form to just make sure that we're not looking at invalid states. So the hybrid algorithms that we used are VQE and QAOA. I won't be describing them in that much detail. Just they're both hybrid algorithms, which means that they perform classical and quantum computations interchangeably in a loop. QAOA is in a way a special case of VQE, with a focus on combinatorial optimization problems, so specifically NP-hard problems. And yeah, they're both relatively new. I think this one's from 2013 and this one's from 2014. A big difference for from the use case perspective, from a user's perspective, is that the number of parameters that gets optimized in each of them is different. So with VQE, we have the number of parameters that gets optimized in each iteration is dependent on the number of qubits and on this extra parameter that's defined, and it's called reps. So it's both of them. Like the larger the problem, the more parameters there are, and also we have this parameter reps that sort of dictates not necessarily the accuracy, but the idea is that if you make it larger, the results should hopefully be better. It's not always the case, but yeah. And then for QAOA, the number of parameters that gets optimized isn't dependent on the number of qubits. It's only dependent on this parameter that's called P, and P dictates how many times this portion is repeated. So basically, here we're applying these two operators, and we do the whole thing P times. So we have 2P parameters. This is a big difference because choosing a good initial point, so good initial values for these parameters is important. It has a big influence on the quality of the results. So we focused on trying to see, trying different initial points and stuff like that. So it was quite important for us that the number is very different. We looked at 3 types of encoding, as I already mentioned. It might be the easiest to just describe them using examples. So we have a simple example here where we have 4 people and their favorite colors. It's not possible to encode these colors as strings on a quantum computer. So that's why these 3 types of encoding were used by us. The first encoding is one-hot encoding. I'm pretty sure that everyone has heard of it. What happens with one-hot encoding is that each possible value gets its each possible class, I guess, gets its value, like numeric value, and then each option gets its separate column. And then, so in this case, right, the color is 0. We assume that it's the 0th option. So in this case, in the 0th or first, however we index this, in the first column we have a 1, right? And then for green, it's maybe let's try. Yeah, for blue, if we say that it's the 3rd category, we'll have a 1 in the third column and not in the other columns. It's very easy, not that easy to explain apparently. And yeah, so this is the interpretation, and the actual encoding is usually just expressed as a single string. Just the columns are here to make it easier to read. Yeah, also in this example, we assume that there's 5 possible colors, but only 4 appear so there's also pink, but no one likes pink apparently. Weird. So yeah, that's one-hot encoding, very, very basic. There's also binary encoding. It's also easy. We also assign numbers to the categories, and then we just encode those numbers as a binary number. So red is number 0, so it's all zeros. Blue was number 2, so we have a 2 here. That's it. Domain wall encoding is a bit weirder, I guess. It's the inspiration for it comes from the world of physics, from the idea of domain walls. And domain walls are these interfaces between neighboring magnetic domains, where the magnetic moments sort of gradually rotate from like one direction to the other. So that's basically the inspiration for this. So if you look at this example, we have like a chain of whatever bits, I guess. So there's 6 bits or qubits, and so there's 5 possible spaces between them. And what we do is we fix the left edge to be a positive energy, and we set the right edge to be a negative energy. And so we know that there has to be a spot where the energy will switch from positive to negative, right? So we could have positive, 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 and then starting from here, negative, negative. So in this case, the wall would be here, right, where the pluses turn into minus signs. Because of this, we can actually save 1 bit. Sort of similarly, so if you have a piece of string and you cut it in 4 spots, you end up with 5 small pieces of string, right? Because with this encoding, we don't really derive any meaning from the specific bits. We derive meaning from the pairs of neighboring bits, so from like the walls between the bits. So in this specific example, so yeah, so when I said positive and negative energy, let's just now instead of positive energy, let's just say we have 1s, and for the negative energy, let's just say we have 0s, right? So in this case, we only have 0s in this vector. And so we know that the energy turned from positive to negative at the 0th index, right? Because it's just already 0s, like there's no 1s. And in this case, we see that the energy turns from positive to negative at the 3rd index, because we have 0s all the way up. We have 1s all the way up to here, right? Yeah. So we don't. In this case, we don't look at the specific bits. We look for the spot where we stop seeing 1s and we start seeing 0s. And in a correct domain wall encoded vector, we will only have 1 wall. So it's impossible for it to be, I don't know, 1 0 1 0 1 0. That would be numbers like multiple walls, and there has to only be 1 wall. Yeah. So that's domain wall encoding. And the types of encodings have their advantages and disadvantages. The biggest, most obvious one is the number of bits needed to encode n values. With one-hot encoding, it has to be n, because yeah, we need as many values as many bits as possible values. With domain wall, as I said, we're saving 1 bit, and with binary encoding, it's just logarithmic. There's no magic to it. What's also important is the maximum order needed to decode single values. For our purposes, it's actually this actually means that the actual interpretation of this weird phrase is that, so when we see the output vector of the algorithm, we have to convert it to this matrix somehow, right? Because this matrix is what we need for our formula. And with one-hot encoding, so just this type of encoding, it's very easy to convert this vector and these vectors into this matrix, right? Because this is basically already a one-hot encoded matrix. We see a 1 if a specific task is to be run on a specific machine type, and 0s otherwise. So there's no conversion that really needs to happen. With binary and domain wall encoding, it's more complicated. to plug in those vectors into this function, we need, like, the computations are a bit more complicated. With binary encoding, it's specifically complex, and the polynomial actually also scales logarithmically. This is something that Adam Gloss, I believe, asked about 2 weeks ago. He was asking if the polynomial was constant, like had a constant order, or if it also grew. And so, yeah, it did. And with domain wall encoding in literature, they claim it to be a 1. It's not really a 1, to be honest. I mean, the polynomial, this is true if we ignore infeasible states, basically, because it's possible for, as I said, a correct domain wall encoded vector will only have one wall. So, for instance, a vector that would have a 1, 0, 1, 0, that would be incorrect. And if we use this polynomial of degree 1, it doesn't really handle invalid states. So we needed to square some stuff, and we ended up with realistically polynomials of like the second degrees, right? So quadratic function, but it's not really described that way in literature. Yeah, so that was the most important thing to us, actually. And yeah, here's an example of how these encodings looked for us on like a very, very small example. So with one-hot encoding, we just have the like little parts that correspond to each task. And then we have the slag variables. So in this case, the first task would be run on the, first machine, assuming we index from 0. This is very confusing. Why are we like this? Well, this is the first machine, this is the second machine, this is the third machine, right? So the first task would be run on the first machine, the second task on the 0th machine, and the third task on the first machine as well. Here we have the same thing, but just expressed as binary encoding. So it's also it's also 1, 0, and 1. And with domain wall encoding, it's also the same. So we can see that these encodings are more dense. It would be even more noticeable if it was if there were more machines, because binary encoding would always have the smallest vector, because it's the most dense out of the 3. And as I mentioned, we also utilized QAOE mixers. QAOE mixers are this operator that's used to move through the configuration space. When I was showing you this, basically the mixing operator is here. So we have the cost operator and the mixing operator. The cost operator is directly related to the objective function, and the mixing operator is a different thing. It's just used to move through the configuration space and try different states. And so the mixer that's used by default is the X mixer. And so the X gate, as you probably know, is just the negation gate. So with the X mixer, we basically, if we're in this state, so 0, 0, 1, 0, 0, we can move to any state that's created by negating any of the any bit, right? So if we negate the first bit, it's going to be 1, 0, 1, 0, 0, and so forth. So these are the options we can go to. And so if we assume this to be a one-hot encoded vector, the states that we can transition to are all incorrect, right? We don't end up at a one-hot at a correct one-hot vector this way at all. Like it's not possible. So there's certain encoding specific mixers that can be used that make it possible to only consider feasible states. So for one-hot encoding, there's a mixer that's called XY. And so it uses X and Y gates. And yeah, what it does is basically works by moving the one that we have either to the left or to the right, or like by swapping neighboring bits. In this case, so if we swap these two, we'll end up in this state, and if we swap these two, we'll end up in this state, and if we swap the zeros, nothing happens, and we stay in the same state. So that's this mixer XY, and domain wall encoding also has its custom mixer. It was described in the same paper as the encoding was introduced in. It was, I don't remember what year it was, but it was a paper by Nicholas Chancellor, I'm correct. And he also introduced this mixer. Yeah, and this mixer just works by moving the wall either to the left or to the right by 1. So here if we move the wall to the left by 1, we end up in this state. And if we move the wall to the right, we end up in this state. And so using these mixers, it's possible to only stay in the feasible subspace without moving to these invalid states. And for binary encoding, there isn't really a way to do that as far as we're aware. But with binary encoding, it's possible to eliminate invalid states at all, right? If we want to, as I said, if we want to encode four options using binary encoding, we're using up all of the options. There's no invalid options. The only issue appears when we want to encode, for instance, something that's not a power of 2. So if we want to encode 3 states, three possibilities using binary encoding, we'll be using 2 bits, and there will be 1 state that's infeasible. So it also has to be penalized, but it's less of an issue than for 1-hot and domain wall, because these really generate a lot of infeasible states. Okay, now we switch presenters.
I think you have to stop sharing, yeah.
Yeah.
Can you see it? Yes. Can you see it?
Not yet. At least I don't see your slides.
Now should be fine.
Yes. Yes, I can see your slides. Great.
Great.
All right.
So, okay. So when it comes to experiment design, they were designed in the following way. So for each of 3 encodings, 1-hot, domain wall, and binary, we were testing 3 algorithms variants. It was QA/UA with default X mixer, and it was done for all 3 encodings. We were testing as well QA/UA with custom mixer that was dedicated to the given encoding, and as Julia said, it was only possible for 1-hot and domain wall encoding, and VQE for all 3 encodings. Now, for each such combination encoding and algorithm, we were testing the internal parameters of the algorithms, meaning the P parameter and reps parameter for VQE and QA/UA. And these parameters were ranging from 1 to 3. Then for each such combination encoding variant and parameter, we were testing 4 classical optimizers. These are Kobila, LBFGSB, Nelder-Mead, and Powell. Each experiment was repeated 1,000 times to get the best averages. And each such repetition out of those 1,000 is measuring the quantum circuit 1,024 times, which is known as the Schotz number in the Qiskit library. Since there were many experiments to be run, we were conducting them on the Prometheus supercomputer. When it comes to tested problem instances, we were basing our work on a master's thesis of our colleague, and we decided to extend the experiment a bit to introduce a problem instance that would be a bit more advanced. So as in the previous thesis, we as well tested smaller problem instance that contained just 1 path and 3 tasks and 3 types of machines. And as well, we decided to introduce, let's say, a larger instance that contained 2 paths, 4 tasks, and 3 types of machines. And this larger problem instance was designed in a following way that it would fit into 15 qubits. As at the time when we were planning our experiment, 15 qubits was the limit of the largest publicly available real quantum device. So we have to somehow fit into those 15 qubits because we were planning to to compare our results from simulator and from real quantum device. And unfortunately, for this larger instance, we were not able to design the problem in such a way that the one-hot encoding would fit into it. So we were able only to run one domain wall and binary encoding for this bigger instance. And based on the enumerations from the previous slide, for the smaller instance, we run 96 experiments. And for the larger instance, we run 60. And now when it comes to types of solutions, usually when you read the literature about the solving optimization problems, you see optimal and correct or incorrect sometimes solutions. But in our case, when we were at the very beginning of our experiments analyzing the results, we spotted that this might not be enough. So maybe let's briefly describe those solutions, those metrics that we introduced. Of course, there's this optimal solution, right? The one that we are looking for. So the solution that fits within the deadline and costs the least. Then we have correct solution. So a solution that is representing a valid vector. So a vector correct with regards to the given encoding and fits within the deadline. So it's not the optimal solution, but it's correct. Assuming the deadline is, I don't know, 5 hours, a correct solution would take either 5 minutes or 4 hours, doesn't matter, but it just has to fit within the deadline. Something that we introduced is a semi-optimal solution. So this is a solution that the part of assigning the tasks to machines is identical as in the optimal solution vector, but only the slack variables are incorrect. Same for semi-correct solution. So this is a solution with the part of assignment that has the same part as correct solution vector, but only the slack are incorrect. And then there is the last metric, incorrect solution. And here we have, let's say, 2 parts. We have incorrect feasible. So a solution that is a correct vector in the given encoding. For example, in one-hot encoding, a vector that contains a single 1. But as well, we can have the most incorrect solutions out of all of these. So incorrect, infeasible. So for example, for the one-hot encoding, it would be a vector containing more than single 1. Now this is something that we would like to have in our problem. We would like to have so-called, let's say, ideal ordering. We would like to have firstly optimal solutions, then semi-optimal, then correct, then semi-correct, then incorrect, but still feasible, and at the very end, infeasible. I mean, that's how our, let's say, logical approach to that, it's how we would imagine those weights of those solutions. But it's actually not the way it really looks like. So as I said, at the moment when we were planning or starting our experiments, we were looking at the weight returned by our model. And we were looking at let's say, how the energies are looking like at such a diagram. And what we spotted at the very beginning of our experiment is that these energies can perform or can create something what we call naive ordering. And in this ordering, of course, we are trying to pick up those weights A, B, C that Julia was showing in an equation. So we are trying to pick those weights A, B, C in such a way that at the very beginning we have optimal solutions and then correct solutions. But then what happens is that we have solutions from different metrics mismatched. So we can have, for example, infeasible solutions, energy, before semi-optimal solutions. And this is something what we would not like to have, because those infeasible solutions are, as I said, the most unwanted ones. They have no logical meaning. For example, here you can see an infeasible vector. And let's assume that this is one-hot. So this means, this first part of infeasible vector, that the first task is assigned to 2 machines. So this is completely wrong. So we would like to have energies of such solutions at the very end. And this is something what we call feasibility jump. And in this feasibility jump, we are basically, we have energies of optimal, correct, semi-optimal, semi-correct solutions, and incorrect, feasible. And at the very, very end, we have the energies of infeasible solutions. So those solutions that do not have, let's say, a logical meaning in our problem. Now, when it comes to the impact of choosing the ordering of those solutions, maybe let's just say at the beginning that all of the diagrams that I will be showing are presented in the form of box plots. We chose to use box plots because they are easier to analyze. We can see what are the ranges of the results and so on. So that's why we chose box plots. What you can see in this diagram, on y-axis, we have the percentages of incorrect solutions. And the first 4 results are for naive ordering, and those 4 are for the feasibility jump ordering. And now this diagram is coming from smaller problem instance, and it is for VQE algorithm with one-hot encoding. And what we can see is that for Kobyla algorithm, simply after switching from naive to feasibility jump ordering, the median percentage of incorrect solutions decreased around 8 times. So it decreased from around 83 to around, let's say, 7%. And based on that, we decided to run all of our experiments using this feasibility jump ordering because it simply gave better results. So yeah, all the diagrams that I will be showing you are based on this feasibility jump. So in this feasibility jump ordering, we simply we needed to simply change those numbers, those ABC values, so that the energies are ordered in this way. Let's start discussing the results with the smaller problem instance. So here you can see the percentages of incorrect solutions. The results are grouped by the optimizer, and the same optimizer is colored in the same color. So for Kobyla, we have blue. For LBFGSB, we have pink. For Nethermid, we have yellow. And for Powell, we have green. And then, since these are the results for QAOA algorithm, we had to have both results from default and custom mixer on the same diagram because we want to compare them. So for every single optimizer, you have 5 box plots. So we have firstly default mixer results, and we have one-hot domain wall and binary encoding. And then you have custom mixer and one-hot and domain wall encoding. There are no results for binary encoding because the custom mixer is not yet available. And what we can see is that those optimizers share a similar pattern, right? The first thing that we can see is that the worst results are returned by default mixer with one-hot encoding. And it is happening for all optimizers. Then what we can see is that simply switching to domain wall and binary encoding is allowing us to decrease the number of incorrect solutions median by a half. And another thing is that the best results, so the results having the least number of incorrect solutions, is coming from QAOA run with custom mixer that is available for one-hot and domain wall. Yeah, and among all optimizers, we can see that this median percentage of incorrect solutions is less than 10%. And again, we can see this a similar pattern between all optimizers. Now, when it comes to VQE, the first thing to see is that the results have higher variance, and that results are differing among all 4 optimizers. So we can say that VQE is strongly optimizer dependent. The best results are for Kobyla optimizer and Powell optimizer. So we can say that these 2 are working the best with VQE. And when it comes to, let's say, overall result of VQE, we can say that it is Powell optimizer and domain wall and binary encoding that worked best. Since median percentage of incorrect solutions that they returned is near to 0. Now on this diagram, it's hard to say whether it's domain wall or binary encoding that performed better, but it can actually be seen on these diagrams. And here we are showing you the percentage of correct solutions. And yeah, let's maybe start with VQE on the right side. So you can see that for Powell optimizer, binary encoding returned greater number of correct solutions. So we can say that it outperforms domain wall in this case. And again, when comparing these two algorithms, QAOA and VQE, VQE performed better. For QAOA, we can again see this pattern that using domain wall and binary encodings with default mixer is improving the results, but switching to a custom mixer is improving them even better. And for VQE, well, we can see the higher variance of the results. Yeah, and the fact, maybe to sum up the smaller problem, the best results for the smaller problem instance were returned by VQE, Powell optimizer, and binary encoding. So this last box plot on the right side. Now, one important thing about running the experiments on a real quantum device. We were planning to run the best samples coming from quantum simulator on a real quantum device. And we, especially for that, we were designing our problem to fit into those 15 qubits. However, somewhere when we were finishing our experiments, this largest publicly available real quantum computer was switched off. So we had to take another approach. And what we decided to do is that we will simply pick the best samples and then run them again on a quantum simulator, but with a real noise added, with a noise coming from a real quantum device. And what we can see for VQE, obviously we are expecting the results to get worsen, but there are some conclusions here. So let's maybe analyze the impact on using the feasible metric. So for VQE, we can see that the number of feasible solutions decreased around 3 times, right? Just after using this noise model. For QAOA, it got even worse. So it decreased around 10 times. Now, the important thing here is that these results for QAOA are coming from the experiments with the custom mixer. And now custom mixer is resulting in more gates, and this results in bigger decoherence. And we think that it might be that this error coming from additional gates is the reason why the results got worse for QAOA when comparing it to VQE. So it might actually be a kind of a question whether the custom mixer would indeed perform better than the default X mixer when run on a real quantum device. Because when run on a simulator, then custom mixer is performing better. But what would happen on the real quantum device, this is still an open question. Now, when it comes to the larger problem instance, and again, here we were not testing one hot because simply it did not fit within those 15 qubits. So for QAOA, we again see this pattern. In these diagrams, we are showing you the percentages of incorrect solutions. So we can see this pattern that the best results, so having maybe the worst results, are returned by QAOA run with default mixer. And here we have domain wall and binary. And then simply after switching to a custom mixer that is available for domain wall encoding, the results got better. And this pattern is happening for all 4 optimizers. When it comes to VQE, we again see higher variance of the results. we see that VQE is highly optimizer dependent. And we can say that for 3 out of 4 optimizers, so for Kobyla, LBF, GSB, and Nelder-Mead, binary encoding performs better than domain wall. For Powell, these medians are not that differing, so it's hard to say, but for 3 out of 4, it's binary encoding that performs better. And again, something to see here is that those differences between QAOA and VQE are not that high as in smaller problem instances. So when you look at Powell for VQE and binary encoding, and when you look at custom mixer and domain wall in QAOA, you can see that these medians are quite similar. So it might be that for larger problem instances, QAOA might actually perform similar to VQE or even better. Now, when it comes to conclusions of our thesis, the first conclusion is that those alternative encodings to the 100 encoding, meaning domain wall and binary encodings, are even allowing us to run those larger instances of problems. And we had this problem because we had a limit of qubits, and we were simply not able to even run the larger instance using 100 encoding. So this is a huge advantage of those newly proposed encodings. The second thing is optimization problems that are containing inequalities are harder to solve. They are obviously increasing the number of incorrect solutions, and therefore solving them is yeah, as I said, harder, and it maybe requires some let's say adjustments. Maybe there, as I will say in the next slide, there are ways to get rid of those slack variables, because we think that they are actually the reason for not very satisfactory results. Yeah, and they are increasing the number of incorrect solutions. The next thing is denser encoding, so domain wall and binary. Since they are using not as many qubits as 100 encoding, they are reducing the number of incorrect solutions. And this can lead to better results. For example, this could be seen on VQE results for the smaller problem instance. There, the binary and domain wall encodings outperformed 100 encoding. Next thing is the selection of appropriate model parameters, so those weights, ABC. This is crucial, and we have shown that there are a few ways to pick them, and the way you pick them has an impact on your results. So this is something to be experimented. The next thing, and maybe this was not shown on any of the diagram, but it was a goal of our work to test how increasing P and the reps parameter is improving the results. Because in literature, usually it's said that they improve the results. However, in our case, they did not. And the last thing is, as I was saying, when using custom mixer in QAOA algorithm, it might be that actually the results coming from custom mixer might be worse from the default mixer when run on real quantum device, because we have the coherence coming from additional gates. Yeah, and now when it comes to the future work, as I said, the first thing to do is to use methods that are not introducing slack variables. So there are such methods, there are articles on that. Sorry? I cannot hear you. If you could please repeat.
Yes, I think you can go on. There was one person that was unmuted for a while, but
okay,
it was not a question. Mm-hmm.
Okay, sure. Yeah. So as I said, the first thing would be to get rid of those slack variables and just look for some other methods. The second thing to extend to work on would be analysis on how to choose those proper model weights. those in our case, ABC numbers in the model equation. And the first thing would be to investigate the coherence that is coming from the additional gates when using custom QAOA mixer and when run on a real quantum device, because when run on a simulator, then custom mixer is returning better results. When it comes to references, there are a few articles that we are basing on. So the first one is, as Julia was saying, Nicholas Chancellor, who proposed domain-well encoding. Then we have Adam Gloss, who proposed binary encoding. The first article from that article, we were basing our operators for mixers. So this was our source of knowledge for mixers, for QAOA. The fourth is the master's thesis by our colleague, which we're extending and basing on. The fifth one is our master's thesis, and last two are as well thesis and an article from our colleague who was investigating job scheduling problems, but on a D-Wave computer. And that would be it regarding our thesis. Thank you.
Great, thank you. All right, do we have any questions to our speakers? Let me check our chat. I don't see any questions on our chat. Maybe someone would like to unmute and ask. No questions, so maybe I can start. So first of all, thanks once again. It was very good and clear presentation. So you also presented the future work. So as far as I know and understand, you also have a larger team working on this topic, right? In CIFRONet, right? Because you are still working on this topic. Mm-hmm.
I mean, not really the two of us,
Okay.
As far as I'm aware, but I know that Dr. Życesz, also with Justyna Zawalska, she also presented some of her work here. So I know they are working on it in CIFRONet, but that would be, I guess.
Oh, okay.
Dr. Życesz would know more about this.
So it's now some kind of continuation, right, of your master thesis, right? Okay, good. So there's a question from Luis. Do you have any comments about encoding in quantum clustering algorithm? You can check the question.
Yeah. I don't think I've ever looked into quantum clustering, so so I don't really have any comments personally.
Yeah, this was restricted only to workflow scheduling problems specifically.
Okay. Specifically to workflow scheduling. Have you perhaps compared your results with quantum annealing on the D-Wave machine?
Yeah, we didn't do that since that would be like a separate third thesis. But there were people looking into it using the D-Wave machine, so with quantum annealing. I know there was also a thesis that discussed, because like our initial goal was to find ways to encode larger problems. That's how we ended up looking into the encodings. And I know there was also some work done by our colleague for the D-Wave machine to see if it's possible to encode larger problems or to split the problem into like components and then run those. And I think there's like a library, I think it's called D-Wave Hybrid. And I know he was looking into that, but we didn't really compare our results. That can be done in the future, probably.
Okay. And do you know maybe someone is already working on this topic somewhere in Poland or maybe abroad? Because the QPO formulation. Yes. Yeah. Go on.
I mean, Dr. Życesz can probably say something about the two theses. I mean, she's read both, right? So.
So I don't know if you are asking about working on D-Wave or working on workflows. What do you mean?
So you can tell about both, but first about quantum annealing, because that was
okay.
the topic of the question.
David Tomasiewicz actually started with this work with D-Wave, and David managed to run it on even a more, maybe not much bigger, but a bit bigger examples on D-Wave. They fit into the architecture, and he managed to get some results. But these results are still, well, these are still small examples, yes? And we had some, as I said 2 weeks ago, we had some, we did some experiments with D-Wave hybrid, but with new architecture, Pegasus, but it didn't produce better results. But we have now better results from CQM library, recently released from D-Wave. But as we discussed with Adam Głos, and we also think it's the case that this CQM does not use quantum machine so much. Yes, it uses for sure some time on quantum processor because it shows in a logs, but we suspect that most of the work is done actually by classical solvers, because still these problems we are calculating are quite small. But yes, we are still working on that also with annealer. So from the first perspective, I must say that with annealer, if you start with annealer with such problems, you can have much, maybe not much, but a little bigger examples that can fit into architecture, and you can get real results from the quantum machine. But these results are not that that satisfactory that that's the end. Yes, so you can still you have to still search for better settings and better algorithm. So
yeah.
And here what Julia and Joasia did, they actually were using a simulator. And on simulator you can compare these results, and if they run it on a real computer, they didn't have a chance because the computer was switched off. But I don't expect that they would get any real outcome without any this error mitigation. Yes, because
that's also what I expect. Okay,
yeah,
great. Anyway, thanks for clarification. So now we also know the broader context, which is great. There's one more question, which is quite general, I would say, but maybe you can try to answer. A question from Munavar: how you find the size of instances, and how we know the size of instances that will fit to real quantum computer?
Well, we didn't explain that very well, but the size of the problem, it's just the number of qubits that's necessary to solve the problem. And so that depends on the encoding. And then for instance, if we just use one hot encoding, we would need n times m qubits. So the number of tasks times the number of machines. If we use another encoding, it would be fewer qubits. And then we also need qubits for those slack variables. And regarding the second part of the question, the largest IBM computer that's available, I think it's 7 qubits. So that's it. And it used to be 16. We actually designed our problems like specifically for them to be under 16 qubits because we wanted them to fit on the Melbourne machine. And then they got switched off. So we could have done larger examples, but we didn't know.
Hopefully in the future we'll be able to just run experiments with larger instances. But as for now, using simulator is necessity, and it's sufficient. In fact, as Katarzyna said, due to the noise and large errors that should be mitigated. We shouldn't expect that we'll achieve better results on quantum computers. But anyway, on using simulators and classical computers, we can validate our algorithms. All right, do we have any more questions? I don't see more questions on our chat, so let me maybe share my screen once again just to invite you to our next meeting. So first of all, we would like to thank once again our strategic partners, Snarto and Cogit, as well as our honorary partners for supporting us. And we would like to invite you to attend the next meetup, episode 37. It will be on 14th of March. So and the lecturer, the instructor is Aleksandra Lipinska, and this lecture will be indeed about error mitigation, about error correction codes. So it's also related a bit to the last question from our discussion. So yeah, I think that it's might be very interesting. So we invite you to join. We hope that you will join also our next events. So if you want to stay up to date with our events, we invite you to join our groups, Facebook group, to follow our fan pages, channels, profiles on Twitter, LinkedIn, or our website. You can find information about the contest of popularizing quantum computing and the workshop on quantum programming that we are organizing now. So it will start in 1 week from now. And I think that's it for today, at least from my side. So I don't see more questions on our chat. So with that, I would like to thank once again our great speakers. Thank you, Julia, Joanna, and we hope to see you next time on our next events. Take care.
Everyone.
Thank
Bye.
you. Bye-bye.
Bye.